It's 15 degrees below zero outside. The furnace hasn't turned on in almost 2 hours, and yet this room is warm. Not blazing hot, not summer comfortable, but definitely warm enough that you don't feel the cold creeping through the walls. And the heat isn't coming from a heater, it's coming from that box mounted on the wall. A simple wooden box, about the size of a window, filled with rows of aluminum cans painted flat black. No wires running to it, no gas line, no moving parts humming inside, just sunlight hitting the front of the box. That's it. The sun warms the metal cans, the air inside the box heats up, and warm air slowly flows into the room while cooler air gets pulled back in from below. And the entire thing cost less than $8 to build. Now here's the strange part. People have been quietly building versions of these for over 40 years, yet most homeowners have never heard of them. What you're looking at is called a solar air heater. Sometimes people call it a solar can heater because the heat collector inside is made from something most of us throw away every day: aluminum drink cans. This idea isn't new. In fact, people in off-grid communities across Canada and the northern United States have been building these systems since the early 1980s. Cabins, garages, workshops, sheds, anywhere that gets good winter sunlight on a south-facing wall. The concept is simple. Instead of letting sunlight hit your wall and disappear back into the air, you capture that energy inside a small insulated box and channel the heat into the room. No electricity, no fuel, no complicated equipment, just sunlight turning into heat. So why don't more people know about this? Part of the answer is surprisingly practical. The heating and cooling industry generates hundreds of billions of dollars every year selling furnaces, fuel, heat pumps, and HVAC systems. A small box made from recycled cans that produces real heat for almost nothing isn't exactly the kind of product that gets promoted. But once you understand the physics behind it, the idea becomes almost obvious. One of the strange things about modern life is how easily we forget that energy is constantly moving around us. Sunlight hits the walls of your house every single day, even in winter, even when the air outside is freezing. That sunlight is carrying an enormous amount of energy. Most of the time, we simply let it go to waste. The sun warms the siding of the house for a few hours, the surface temperature rises, and then the heat slowly radiates back into the air as the afternoon fades. It happens every day without us noticing, but hidden inside that ordinary process is a small system waiting to be used. Because when sunlight hits a dark surface, the energy doesn't just disappear. It gets absorbed and converted directly into heat. And if that heat is trapped inside a box instead of escaping back into the air, it can start warming the air inside. That warm air rises, cooler air sinks, and suddenly you have a natural circulation loop forming on its own. No fan required, no pump required, just the same physics that makes warm air rise above a campfire. What this simple solar box does is guide that natural movement of heat into a room instead of letting it drift away unused. You've actually seen this effect many times before, even if you never thought about it. Think about a car parked in the sun on a cold winter day. The air outside might still be near freezing, but when you open the door a few hours later, the inside of the car feels noticeably warmer. The same thing happens in a greenhouse. Sunlight passes through the clear panels, strikes dark surfaces inside, and those surfaces convert the sunlight into heat. Because the warm air is trapped, the temperature inside the structure rises. The solar box on the wall works in a very similar way. Sunlight passes through the clear front panel and hits the aluminum cans inside. Those cans are painted flat black, which allows them to absorb as much solar radiation as possible. As the metal heats up, the air around it warms as well, and warm air naturally rises. So cooler air from the room enters the bottom opening of the collector. As it moves upward through the columns of heated cans, it absorbs that heat. By the time the air reaches the top of the box, it's significantly warmer. That warm air flows back into the room. The room air slowly cools, sinks, and is pulled back toward the bottom opening again. And just like that, a gentle convection cycle begins, powered entirely by sunlight. The entire heater is surprisingly simple. At its core, it's just a shallow wooden box mounted on a sun-facing wall. Inside that box are vertical columns made from aluminum cans stacked end to end. The cans are painted flat black so they absorb as much solar energy as possible. A clear sheet of polycarbonate or plexiglass covers the front of the box. This acts like the glazing on a greenhouse. Sunlight passes through the clear surface and strikes the cans, but the heat that builds inside has a harder time escaping back out. Two openings connect the collector to the room. One near the bottom allows cooler air from the room to enter the box. Another near the top allows the warmed air to flow back inside. As the sun heats the metal cans, the air inside the box warms up and begins to rise. That rising air exits through the upper opening and enters the room. At the same time, cooler air from the room is pulled into the bottom opening to replace it. The result is a slow but continuous cycle of air moving through the collector, picking up heat from the sun and delivering it back into the space. No electricity, no mechanical parts, just sunlight and the natural movement of warm air. The materials for building one of these collectors are surprisingly simple. In fact, most of them are things you can find at a hardware store or even in a recycling bin. The most important component is aluminum cans. For a collector around 3 by 4 feet, you'll usually need somewhere between 100 and 140 cans. That might sound like a lot, but they're incredibly easy to collect. Ask a neighbor, a local bar, or a restaurant, and you'll often get a full bag in a single afternoon. Next is the frame. A shallow wooden box made from simple lumber works perfectly. Boards around 1 by 6 inches create enough depth for the air to move through the collector while keeping the structure lightweight. Scrap wood works just fine here. You'll also need flat black spray paint. The cans and the inside of the box are painted black because darker surfaces absorb much more solar radiation than lighter ones. A tube of silicone caulk or construction adhesive will be used to attach the cans together into vertical columns. Finally, the front of the box is covered with a clear sheet of polycarbonate or plexiglass. This allows sunlight to enter while trapping heat inside the collector. Add a bit of weather stripping around the edges to seal everything tightly, and the materials list is complete. In total, if you collect the cans for free, the cost can be surprisingly close to $8. Putting the collector together is mostly a matter of preparation and patience. Start by cleaning the aluminum cans thoroughly. Any residue left inside can create odors once the cans begin heating up in the sun, so it's worth rinsing and drying them completely. Next, remove the tops and bottoms from each can. A standard can opener works well for this. Once both ends are removed, each can becomes a small open cylinder that allows air to pass through freely. The cans are then stacked vertically, one on top of another, forming tall columns that will run the height of the collector box. A small bead of silicone or construction adhesive between each can is enough to hold the column together. Once the adhesive cures, the entire assembly is painted with flat black spray paint. 2 thin coats usually provide good coverage. The goal is to create a surface that absorbs as much sunlight as possible across every part of the collector. After the paint dries, the can columns are placed inside the wooden frame and secured so they remain upright and evenly spaced. 2 openings are then cut into the back of the box, one near the bottom for the cold air intake and one near the top for the warm air outlet. Finally, the clear polycarbonate sheet is attached across the front of the box and sealed along the edges. At this point, the collector itself is finished and ready to be mounted on a wall that receives strong sunlight during the day. Now, the collector we just built works perfectly well on its own. Warm air rises, cooler air enters the bottom opening, and the convection cycle keeps the air moving through the box. On a sunny day, that natural airflow can already deliver a noticeable amount of heat into the room. But there's a small upgrade that can make the system significantly more effective. And the best part is that it doesn't add much complexity or cost. Instead of relying only on natural convection, you can install a small computer fan near the outlet of the collector. The kind used in desktop computers works perfectly for this. These fans are easy to find in old electronics, thrift stores, or surplus shops. To power the fan, connect it directly to a small solar panel. No battery, no controller, just 2 wires. When sunlight hits the panel, the fan turns on and pushes air through the collector. When the sun disappears, the fan stops automatically. The result is much stronger airflow moving through the heated cans. More air passing through the collector means more heat delivered into the room. Interestingly, it can also improve efficiency. By moving air through the box faster, the collector stays slightly cooler, which actually reduces heat loss through the front glazing. Sometimes the simplest upgrade makes the biggest difference. There's one mistake that shows up again and again when people build their first solar heater. The box isn't sealed properly. At first, it might not seem like a big deal. After all, the collector is producing heat as long as the sun is shining, but even small gaps along the edges of the frame or around the glazing can allow warm air to escape before it ever reaches the room, and once that heat leaks out, it's gone. Think of the collector as a small greenhouse attached to your wall. Sunlight enters through the clear panel and builds heat inside the box. If the air can slip out through cracks along the sides or around the seams, the system loses a large portion of its potential output. The fix is simple. Seal every joint. Run silicone along the interior seams. Use weather stripping around the edges of the glazing. close any small gaps where the air could escape. This usually takes less than 15 minutes, but it can make a surprising difference in performance. The collector will keep producing heat either way. The real question is whether that heat ends up warming your room or leaking back outside into the winter air. At this point, the idea sounds simple enough, but one question usually comes up. How much heat can a system like this actually produce? One of the most detailed real-world examples comes from an engineer named Gary Risa. After retiring from a long career in aerospace engineering, he moved to Montana and began experimenting with different solar heating systems for his workshop. Instead of guessing, he measured everything: temperature differences between the intake and outlet, airflow through the collector, total heat output during winter sunlight. The collector he built was similar to the one we're discussing: rows of aluminum cans inside a glazed box mounted on a south-facing wall. Under typical winter sun, his measurements showed a temperature increase of around 50 to 60 degrees Fahrenheit between the air entering the bottom of the collector and the air exiting at the top. At peak output, the system produced roughly 25,000 BTU per hour. To put that into perspective, that amount of heat is comparable to burning about 2 gallons of propane over the course of a clear winter day. And all of that heat came from sunlight striking a simple box of recycled cans mounted on the wall of his workshop. No fuel deliveries, no power bills, just sunlight doing what it already does every day. What makes this idea so interesting isn't just that it works, it's how obvious it feels once you see it. Every winter, sunlight strikes the south-facing walls of millions of buildings. Even on cold days, that sunlight is carrying a huge amount of energy. The walls warm slightly, the heat radiates back into the air, and most of that energy disappears without anyone noticing. Day after day, season after season, the solar heater simply intercepts a small portion of that energy before it escapes. The concept behind systems like this isn't new either. During the energy crises of the 1970s, engineers spent a lot of time studying passive solar heating, ways to use sunlight directly to warm buildings without burning fuel. For a while, ideas like solar collectors, thermal walls, and passive heating designs became surprisingly popular. Then fuel prices dropped again. The urgency faded, and many of those simple solutions slowly slipped out of public attention. But the physics never changed. The sun didn't change, and the sunlight hitting the south side of your house every winter day didn't change either. The opportunity to use that energy has been there all along. The thing about systems like this is that once you understand them, you start noticing opportunities everywhere. Sunlight hitting a wall, warm air naturally rising, energy moving quietly through everyday environments. Most of the time we simply ignore it because modern infrastructure makes it easy to rely on larger systems, furnaces, fuel deliveries, electric heaters, but sometimes a very small system can capture a piece of that same energy with almost no cost at all. A wooden box, a handful of recycled cans, one sunny wall, and suddenly a part of your heating problem starts solving itself. Maybe you're trying to reduce a heating bill. Maybe you're building an off-grid cabin or workshop, or maybe you're just curious about how simple systems work. Either way, the sun will keep hitting that wall every winter day. The only real question is whether you decide to collect the heat or let it drift away unused. Now you know how.